Good afternoon and welcome. Today I will be talking to you about data. While this might not sound like much fun, it is something that has the potential to improve the workflow of many people attending this symposium. I would like to start by telling you a story. A few years ago, my husband and I took up bird watching. We headed down to Point Pelee for the annual spring migration, and rising before dawn, we joined the throng at the southern tip. I excitedly watched wave after wave of birds appear out of the mists, while the guy next to me looked down his nose and declared, "I am only interested in rare birds." We had a great couple of days. During the afternoon lulls, we explored various ecosystems, contemplated whether there was an escarpment as well as a submerged moraine anchoring the giant spit. Okay, that part was just me. And snacked on birdseed cookies. The other guy didn't look like he had near as much fun. So with that in the back of my mind, let's talk about data. Simply put, we need data to make a model. This applies to quaternary sediments, bedrock, or groundwater flow. Elevation data in the form of a digital terrain model is a critical data set for all subsurface work. Riley's talk will showcase the benefits of a recent explosion of fabulous high-resolution terrain models, and these images of the Grand River show a progressive increase in both spatial resolution and an increase in vertical accuracy over time. We can obtain a lot of information from the seamless GIS products available as free downloads from Geology Ontario or OGS Earth. This slide compares superficial geology, physiography, bedrock formations, surface elevation, and drift thickness for a small area of the Dundas Buried Bedrock Valley. There are many different geophysical methods that can be applied to modeling projects. Over the years, we have used gravity, electromagnetic, and seismic reflection surveys to help find buried valleys and begin to constrain major sediment packages. Collectively, these surveys provide a wealth of information, but we still don't have enough to produce a model. Looking at the more than 46,000 records in the Niagara Peninsula, it is clear that we won't get very far if we confine ourselves to only the highest quality data obtained specifically for the project. Remember the guy and his rare birds? Instead, we need to look to geotechnical records clustered around cities and roads, oil and gas records corresponding to major pools, and by far the most plentiful and widespread, water well records, the sparrows of the modeling world. So how do all of these different data stack up? In the next few slides, we're going to look at examples of data from within a couple of 100 meters surrounding a cored borehole. For each sediment formation, silt and clay are shown in light and dark blue, diamicton in green, and sand and gravel in yellow and red. First, we see data from the superficial geology, soils, and bedrock geology maps. Each one is good for about 1 meter of thickness and has been placed at the correct elevation based on either a digital terrain model or regional scale bedrock surface maps. Next, we see an excerpt from the cored borehole. Notice that there are rather a lot of green diamicton units. As we can see here, geotechnical holes are often shallow and of variable quality, depending on the drilling method used, the purpose of the hole, and the experience of the technician. The first one underrepresents diamicton by quite a lot. The water well records closest to our boreholes tend to default to clay, which is pretty common, especially on the Niagara Peninsula. In the third well, the coarser older till was misidentified as sand. While lower resolution than geotechnical records, the water wells do penetrate more of the overburden. And finally, we come to the oil and gas records. These records describe the full quaternary sequence as drift and may miss the upper few meters of fractured or weathered rock, but do contain a wealth of information about rock lithologies. So which one is going to be best? Well, that's going to depend on both what's available and what sort of model you're working on. Now that we've considered some of the common sources of data, it is time to focus on the geological information found on water well records. This word cloud image was created from the descriptors found in the 3 material fields within the Water Well Information System database. We can immediately see that certain terms show up far more often than others. Classifying each of the 83 descriptors as primarily a rock, sediment, or other term, I did a count of the number of times each was used and was a bit surprised by the results. Sediment words represent 68% of the over 4.7 million terms used, compared to only 17% for rock. Looking at the rock terms first, limestone is the clear winner, coming in at a whopping 45%. Granite is next at 23%. The remaining terms, which are listed around the bottom and right edge of the slide, are only used 3.5% of the time. Is this reasonable? So how do the rock terms compare with current bedrock maps? If we look at the bedrock map colored by primary lithology instead of formation, we can start to assess the distribution of the terms. In this view, the crystalline basement is in coral, limestone in green, dolostone in blue, and evaporites in gray. Map 2 shows the location of granite, and there is the expected concentration over the crystalline basement. We can also see where limestone overlies granite. Map 3 shows the distribution of red and black shale, once again revealing some deeper units. So far, so good. On map 1 of this slide, we see limestone over both limestone and dolostone bedrock. This clearly shows that dolostone is underrepresented. On map 2, we see dolostone and gypsum, as well as instances of blue limestone. And finally, we have the completed map. These simple queries provide a quick and easy indication of problem rock lithologies. On the sediment side of things, clay, sand, and gravel are clear winners. The remaining terms are also well represented, hinting at the complexity within the overburden. When color is added to the mix and the number of unique combinations of terms are queried, a mind-blowing 37,836 combinations are revealed. The top 100 combinations account for 60% of the records, while the remaining 37,736 account for a mere 40%. In an effort to address this problem, MECP and the OGS will be working together to develop a simple nomenclature for describing geological materials on water well records. We anticipate consulting a stakeholder team of well technicians and drillers throughout the process. The project will include creating a common guidance document with simple descriptions, tips for identifying materials, and photographs. If phase 1 goes well, we will consider converting geological materials in historical well records to the new nomenclature. We will have to keep different construction methods in mind. What comes up? Core? Cuttings? Nothing? Not all core is created equal, as we can see from these photos. With only cuttings or poor quality core, the stuff highlighted by the green arrow would probably look like a nice clay confining layer. In reality, it's a bunch of clay ripped up intraclasts in a sandy matrix. Getting back to the matter at hand, another point to consider is the purpose of most wells and what sort of attention is going to be paid to the geological formations while drilling. How invested are people going to be in providing good data? Is there likely to be someone with geological expertise on site? Maybe for the types of wells circled in green. We will have to make compromises. The ideal log will look very different depending on who you are and what you are working on. My ideal is way to the right, but to quote one of my favorite drillers, Abigail, detailed logs belong in a survey database and not on a water well record. I suspect most water well drillers would be happy with the view on the left, while my geologist's heart would be content if we managed version 2. We will need to review current usage and see if there are multiple terms that convey the same meaning. Perhaps the sand term shown in green could simply be replaced by more consistent use of the terms shown in blue. Before engaging in a slash and burn operation, we will also need to consider whether some of those supposedly meaningless terms are actually quite helpful. This proved to be the case in Niagara. Packed, dense, soft, and loose were very helpful when searching for missing tills. We will have to consider how words are commonly used. I asked friends and family with degrees in engineering, geology, and environmental sciences how they would define clay, and this is the range of answers that came back. We can start to gain an appreciation for how important it will be to provide clear, simple, and meaningful definitions and back them up with photos. Given that we are rapidly approaching 900,000 wells, one could ask, why bother improving new records? The simple answer is that huge numbers are being added every year. Fast forward another decade, and I think we will find it was worth the effort. And on that note, any questions?